So lesson 4A is going to be on related rates, which is one of my favorite topics because they're kind of like big puzzles that you have to figure out and find a way to find what you want using what you're given. So there are going to be some formulas that you're going to have to use in some of these problems. A lot of them you should be very familiar with. So we have circle formulas, area, circumference. Know that circumference can also just be pi times the diameter. You can change it to look like that. Rectangular prisms, these are just like your boxes, kind of length times width times height. If it was a cubic, like a cube, it would be just the side cubed. Triangles, Pythagorean theorem, and the area of a triangle. There's some other stuff about triangles that I'm going to write down on the next slide. Dealing with the right triangle trigonometry, that's going to be important. Cylinders, we have lateral surface area and surface area. I'll explain what those things are in a minute. Spheres, we have volume and surface area, and then right circular cones. We're not going to have like other circular cones usually in this unit. Most of the time they're right circular cones. One other thing that's not really in here is our pyramids. But pyramids are very similar to right circular cones. If we happen to come across a pyramid, it's going to be 1/3 as well. This can also be written as volume equals 1/3 pi r squared h. Your pyramids, so your right pyramids, the volume is going to be 1/3 the base area times the height. So B is base area times height. Now the base could be a triangle, the base could be a rectangle, could be whatever, but it's the base area. So B equals base area. I don't think that one comes up in any of these examples, but if you ever come across it. Now lateral surface area and surface area. So surface area is when you add up the areas of all the sides, which is kind of explanatory. Lateral surface area is like the distance kind of around, like, or the area around the shape, if that makes sense. So for a cylinder, like you have the circles on the top and the bottom, but you have this rectangle that's wrapped around like the vertical side of the shape. So if you were like to take a cylinder and open it up and lay it out flat, it would actually look something like this, right? You would have your top and your bottom, but you would have that rectangle that wraps like around, like essentially like a can shape almost. And the lateral surface area is just the surface area of like the side, that big rectangle sheet. In a right circular cone, the lateral surface area, if you were to unroll a cone, you would have kind of this like curvy cone shape, and then you would have a circle. The lateral surface area is the area of that cone shape. So it just takes away like the bases, essentially, and it's the other part, the surface area of the other part of the shape. So some other additional formulas that you're going to want to know are your right triangle trig formulas. And then also triangle similarity. We use that one a lot. So you have your right triangle trig. I'm going to say ratios. We're going to go back through all of those. And then we use similar triangles a lot. So similar triangles. And I'm going to draw two similar triangles. We're going to have big A, big B, and big C. And then we'll have another similar triangle similar to that one. That's going to have little a, little b, and little c. So these are similar triangles. So ABC triangle ABC is similar to triangle ABC. All right. Well, I named it by its sides, not as vertices, but you get the drift, okay? So if they're similar, their sides are going to be proportional. So like big A over little a is going to be equal to big B over little b. And that's going to be equal to big C over little c. So just that relationship is important. We're going to use it a lot. Now, right triangle trig ratios. So sine in a right triangle, sine of theta is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Okay, those are ones that you've probably seen before. So, ka, toa. Okay, remember those. But the inverses, or not the inverse, the reciprocals. So secant's reciprocal is sine's reciprocal is cosecant. So if we have cosecant, it would be hypotenuse over opposite. Secant is going to be hypotenuse over adjacent. And cotangent would be adjacent over opposite. Okay, so we're going to be using those sometimes in these problems. Really, any formula that you've learned in geometry could pop up in some of these, and then some that they just give you. And a lot of times they'll give you like the surface area formulas in the problem and stuff like that. All right. So we're going to jump into some examples. First, just like we're kind of introducing you to what related rates is, but then jumping into those geometry problems where we use a lot of these formulas. All right, so we're going to jump into our first example. So when you read this problem, we have suppose two functions are related by the equation y equals x squared plus 3. Find dy dt when x equals 1, given that dx dt equals 2 when x equals 1. Now, you may be thinking, there's no t's in this equation. So related rates is about finding a rate. So what we're actually finding is we're finding how y is changing with respect to t, which is time. So this will make more sense like in the other problems that are more about like things you can actually picture. But we're going to find the derivative of this function with respect to t instead of with respect to x or y, because we're trying to find like the rate of the function at a specific or the way the function is changing at a specific x value with relation to t, which t is time. So when we're doing related rates, we're actually going to be doing implicit differentiation, because when we're finding the derivatives of these functions, we're going to be finding the derivatives with respect to t. And most of the time, they're not going to have a t in the function. Now, every now and then there will be one if it's like a function that is related to time. But most of the time, there's not going to be a t in the function. So every time you're finding the derivative with respect to t, or finding like dx dt, dy dt, dv dt if we're talking about volume, or dA dt if we're talking about area, there'll be a lot of different problems that we're dealing with. We're going to be using implicit differentiation. So here is my function, y equals x squared plus 3, and I'm going to be finding the derivative with respect to t. So I'm going to be finding derivative of y with respect to t, the derivative of x with respect to t. So I'm finding dy dt, dx dt, and those types of things. So when I first find the derivative of y here, so the derivative of y is going to be 1 times dy dt. So I'm technically finding the derivative of every single term. So it'll be 1 times dy dt, or you can just write dy dt. And then the derivative of x squared is going to be 2x times dx dt. And the derivative of 3 is just going to be 0, so that term is going to disappear. Now, we were trying to find dy dt when x equals 1 and when dx dt equals 2. So those are going to be the values that I'm plugging in here for x and here for dx dt. So dy dt is 2 times 1 times 2. So dy dt is going to be 4. So when x equals 1 and when x is changing at a rate of 2, 2 what per what, we don't know, 2 units per second maybe, then dy dt is changing at a rate of 4. So that's kind of what you found. Now, again, when we find it in context with other problems, it'll make a little bit more sense. So I'm going to go through the process that you're going to take when you approach these problems. So the method for problem solving, specifically with related rates. You're going to identify everything you're given in the problem and also what you're trying to find. So that's one of the big things with these problems is identifying what you're given and rewriting it in a sense that makes sense with like the equations, and then also what you're trying to find. A lot of these are going to be about pictures or shapes, geometry-based problems. So you're going to want to make a sketch. I always encourage you to make a sketch unless it's related to like a function, like on a graph or something like that, then that one's not as important. But if it's related to like a shape, like a geometric figure or like a person walking, creating a shadow, anything like that, you're going to want to make a sketch of what's going on. You want to write the equation involving the variables whose rates of change are either given or to be determined. So you're going to have to figure out a lot of times what formula you're going to be using. So look at what you're given, look at what you're trying to find, and think about a formula that connects those two things. So if you have volume and a radius, and you're talking about a sphere, obviously the volume of a sphere is going to connect those two values. So you're going to have to figure out what formula you're going to be using if it's not given to you in the problem. And then sometimes you're going to use the chain rule to implicitly differentiate both sides of the equation with respect to time. And then sometimes you're going to have to do like a separate equation as well. So like, for example, if you're doing a problem about a sphere and you're left with a dr dt, but you have some information about the circumference along like the diameter, and you can then figure out what dr dt is based on other information you're given. Sometimes you'll have to do 2 different equations and use both of them to solve the problem that you're given. And then you'll substitute given values in and solve for the required rate of change. A couple of things here. If you have units, provide units. Okay, that's going to be important. Okay, especially if you have related rates in a free response question, you're always going to want to provide units. So let's go ahead and look at a problem that involves geometry. So a pebble is dropped into a calm pond, causing ripples in the form of concentric circles. So it's like a circle within a circle within a circle. So you have the ripples going outward. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? So we have some information about the radius and what it's changing by. We also are trying to find the rate of change of the area. And we have specifically at a time when the radius is 4 feet. So I'm going to go ahead and sketch a little picture here, and I'm also going to list out all the information that I have. So we have the radius of the outer ripple is increasing at a constant rate of 1 foot per second. So that is actually dr dt. So that's the rate that the radius is changing. So that's 1 foot per second. And then we're trying to find the rate of the change of the area. So we're trying to find dA dt. That's our question there. That's what we don't know. And specifically how the area is changing when the radius is equal to 4 feet. Okay, so I'm going to go ahead and draw a little picture here. So I'm just going to draw like one circle. I know we have like several, but we're talking about the outer circle essentially here. So I have one circle. Okay, there would be ripples in the middle, but we're just talking about the outer radius. And we have the radius here. And we're talking about when the radius is 4, what is the area of this whole circle changing by? That's what we're trying to find. Now, here's a couple of things. When you start with a given formula, unless something is not changing, you cannot plug it in from the beginning. So that radius, this radius is changing. Okay, it starts out as a smaller radius and is growing. So that 4 is an instance in time. It's not always 4. So we're not going to plug that 4 in until the very end. Now, if you are like talking about, I don't know, the height of a cone that was like an actual like solid object, the height of a cone, and you knew what that was, and it wasn't changing, you could put that in from the get-go because it has a constant rate of change. So the derivative of it would just be 0. But for this one, you're not going to plug that r in until we get done. So the other thing we want to think of is what is the formula that relates all these things to each other? And for me, I have the area and the radius, which is and we have a circle. So we're going to use the area of a circle formula. So area equals pi r squared. All right, and now I'm going to take the derivative of this formula with respect to time. So I'm going to go ahead and find the derivative of a, which is 1 times dA dt. So I'm just going to write dA dt. And that's what we're trying to find. So hopefully we'll be able to figure out what that is in the end. Then I'm going to have 2 pi r times dr dt. Now, when you look at what we have left here, we're trying to find dA dt. So this is our unknown. And then we have r. We know r is 4 at this instance in time that we're trying to find. And we also have dr dt, which is 1 foot per second. So I'm going to go ahead and plug all those values in. I'm going to plug in the units with the numbers when I plug them in. You can do this. It helps me figure out what my final units are going to be, or you can leave it out. If you choose to leave it out, just be careful and make sure you have the correct final units when you get done. So dA dt equals 2 pi times 4 feet times 1 foot per second. And then I'm going to have 2 times 4 times 1, which is 8. So I'm going to have 8 pi. Then I have feet and feet here, which becomes feet squared per second. So the area of that circle, when the radius is 4, at that instantaneous moment in time, the instantaneous rate of change of the area is 8 pi feet squared per second. So that's what a related rate is. You have one rate and you're finding the rate of something else, and those two things are related to each other. All right, so now we're going to do a problem that already has a picture with it, so we don't have to picture what's going on. We already have it here. We have an airplane flying at an altitude of 6 miles along a flight path that would take it directly over a radar tracking station. If S is decreasing at a rate of 400 miles per hour when S equals 10 miles, what is the speed of the plane? All right, so we have to think about this. And specifically, think about what the speed of a plane is and what decreasing at a rate of 400 miles per hour means. So we already have this triangle drawn for us, which is nice. We don't have to figure out what the shape is. The airplane has a height of 6 miles. That's not going to change. The thing that is changing is this length and this length as the airplane gets closer to being directly above that radar station. So this right here is going to remain constant. So that's what I was saying. There's certain values you can plug in from the get-go and certain values that you have to wait and plug in at the end. That 6 is okay to go ahead and put in there into the formula, whatever formula we decide to use. So I know that the S, this length right here, is decreasing at a rate of 400 miles per hour. So ds over dt is decreasing. So negative 400 miles per hour. S is going to be 10 miles. Okay, that does change though, so we're not going to put that in until the end. And then we're trying to find the speed of the plane. So the speed of the plane is going to be related to this x. It's actually going to be dx dt, the absolute value of that, because speed is always positive if it happens to be negative. But we're looking for dx over dt. That's what we're trying to find, which would be the speed of the plane. Now, when I look at this picture, I see a right triangle. So a right triangle, the sides of a right triangle are related by the Pythagorean theorem, which is a squared plus b squared equals c squared. Now, in this particular picture, I'm going to adjust it to match up with what's in the picture. And one of my legs is x, so I'll have x squared. One of my legs is 6, and that's not changing, so I'm going to go ahead and plug in the 6 squared. And then one of my legs is s squared. Now, I know that s is going to be 10, but that value is changing. Okay, s isn't always 10, so I'm not going to put that value in now. The only value I can currently put in now is the 6, because that 6 miles that the plane is up in the air for this problem is not changing. It's having that constant altitude. Now, I'm going to go ahead and write my formula. So x squared plus 36 equals s squared. And I'm going to go ahead and find my derivative with respect to t. So I'll have 2x times dx dt plus 0, because that's not changing, equals 2s times ds dt. So now I can go ahead and plug in everything I know. Now I know that s is 10. And I know that ds dt is negative 400 miles per hour. Okay, 10 miles actually for the s. I'm trying to find dx dt. That's my unknown. But that still leaves me with one variable that I need to be able to plug in order to find dx dt. Now, I have to figure out what x is going to be when s is 10. So I'm going to draw a little picture right here over to the side. Okay, so we're talking about the moment in time when s is 10. This is still going to be 6. And I'm trying to figure out what x is going to be at that particular moment in time. So I'm going to use the Pythagorean theorem, not the one that I've taken the derivative of, but the original one. So I have x squared plus 6 squared equals 10 squared. So I have x squared plus 36 equals 100. If I take away 36 from 100, I'm going to get 64, which means x is going to be 8. So I know that this value is going to be 8 miles specifically. So I'm going to go ahead and plug in everything I know. So I have 2 times 8 miles times dx dt, which is negative 400 miles per hour, equals 2 times, whoops, I plugged that in the wrong spot. Sorry about that, y'all. We don't know dx dt. I plugged in ds dt. So dx dt is what we're trying to find. Equals 2 times 10 miles times negative 400 miles per hour. All right, so I have 16 miles times dx over dt equals 2 times 10 is 20, and 20 times negative 400 is going to be negative 8,000, and that'll be miles squared per hour. All right, so now I'm going to go ahead and divide by 16 miles on both sides. So I'm going to divide by 16 miles. Take this and put it underneath here. This 16 miles is going to cancel out one of those miles. So my answer will be miles per hour. And then 8,000 divided by 16 is going to be 500. So dx/dt equals negative 500 miles per hour, which means the speed is actually going to be the absolute value of that. So what is the speed of the plane? The speed of the plane is 500 miles per hour. So 500 miles per hour is going to be the speed of the plane. All right, so now we're going to look at example 4. So air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. So here is our balloon. It's a really bad sphere. I can't really draw a sphere, but I'm just drawing a circle. And it talks about trying to find the rate of change of the radius when the radius is 2 feet. So this is the radius. All right, so the radius, of course, is changing. So that too is not anything I'm going to put down right now because that's something we're just going to plug in at the end. So I'm not going to put that on my picture. dV/dt, so the air being pumped into the spherical balloon at a rate of 4.5 cubic feet per minute, that is changing the volume of the balloon. So dV/dt equals 4.5 cubic feet or feet cubed per minute. And then we're trying to find dr/dt. That's what we're looking for. We don't know what that is, specifically when the radius is 2 feet. So I'm going to use the volume of a sphere formula because that's the volume of a sphere involves both the volume and the radius. So the volume of a sphere is going to be 4/3 pi r cubed. So volume equals 4/3 pi r cubed. So I'm going to go ahead and find the derivative of this. So I'll have dV/dt equals 3 times 4/3, which is actually just going to be 4 pi r squared times dr/dt. And now I just have to plug everything in. So dV/dt is what I'm trying to find. R is going to be 2 feet. I didn't put units on that. So R is going to be 2 feet, and I'm squaring that. And then I'm multiplying that by 4. Oh, no, I already know. Hang on. I already know dV/dt. I don't know dr/dt. So right here, I'm going to take this away and I'm going to plug in this value right here. That's going to be 4.5 feet cubed per minute. All right, so I'm going to go ahead and simplify this. So 2 squared is going to be 4, and 4 times 4 is 16. So I'll have 16 pi feet squared times dr/dt equals 4.5 feet cubed per minute. Then I'm going to divide by the 16 feet squared, or 16 pi feet squared. That's going to bump it down to just be feet per minute. So it'll be 4.5 over 16 pi feet per minute. Now, probably that would be like a decimal, in like a decimal form in the multiple, it was like multiple choice, but I'm just going to leave it like that. But 4.5 over 16 pi feet per minute. Now, example 5. A conical paper cup is 10 centimeters tall with a radius of 10 centimeters. The cup is being filled with water so that the water level rises at a rate of 2 centimeters per second. At what rate is water being poured into the cup when the water level is 8 centimeters? So I'm going to go ahead and draw a picture of this cup. So we have kind of like a snow cone type cup. And the radius and the height of this cone are the same. So it's kind of a wide cone. So I'm going to try to do my best to draw like a kind of 2 scale picture. But I might just be a little bit off. Okay. That's not too bad. So the height and the radius of this cone are both 10 centimeters. So the radius of the cup is 10 centimeters and the height of the cup is 10 centimeters. Now that's the height of the entire cup, not necessarily the height of the water in the cup or the radius of the water in the cup. Then it says the cup is being filled with water so that the water level rises at a rate of 2 centimeters per second. So I'm going to draw some water in the cup. Okay. And this water has a height and a radius. So I'm going to label the height as H and the radius as R. Because that water level is changing, I'm labeling them with our variables. The cup is not changing. That's why I put the 10 there. Then it says the cup is being filled with water so the water level rises at a rate of 2 centimeters per second. So that's the water level, which would be the height of the water. So dH over dt equals 2 centimeters per second. At what rate is water being poured into the cup when the water level is 8 centimeters? So when the height is 8 centimeters, what's the rate at which the water is being poured in? So the rate at which the water is being poured in is changing the volume of that cone created by the water. So that's going to be dV over dt. That's what we're looking for. So when you're pumping air in a balloon, that's changing the volume. When you're pouring water into a cup, you're changing the volume of the water. So that's why it's dV dt for both of those. Now, when I look at what I have and what I'm trying to find, I'm going to be using the volume of a right circular cone. So volume equals 1/3 pi r squared h. But you might notice that over here, I'm dealing with height and not the radius. So when you have something like this where you don't have any information about the other variable, except for we do know that the radius of the entire cone is 10 centimeters, but we don't have anything else. We don't have dr dt. We don't have anything about r when the height is 8. A lot of times you can actually, from the get-go, go ahead and change how the formula looks based on what you already know. So, in the original cone, the height and the radius are equal. Now, does that still apply to the water in the cup? Will the height and the radius be equal? Let's talk about it and see. Now, the whole big cup creates a triangle with the height and the radius, and it's a right triangle. And every triangle that's created from the height of the water is also a right triangle. But are all of those right triangles going to have an equal height and a radius? If we think about it, they all have a right angle. So they all have one angle that's equal. And then they all share this angle down here at the bottom of the cup. So they have 2 angles that are equal, which also means that third angle is also equal. But 2 angles is enough to prove similarity. So when triangles are similar, their sides are proportionate to each other. So if those 2 sides are equal in that big triangle, then in any other triangle that's similar to it, they're also going to be equal. So is height equal to radius? Yes, it is. Okay, and that's by angle similarity. So I'm going to go ahead and rewrite this piece of my formula and replace r with h. So it's going to become volume equals 1/3 pi h cubed, because technically I'm replacing this r with h. That's h squared, and one more h makes h cubed. So now My formula is all about H's because I was able to show that relationship between R and H and prove that they were equal to each other. So now I'm going to take the derivative of this formula. So dv dt, which is what I'm trying to find, equals 3 times 1/3, which is 1 pi h squared times dh dt. Now I'm going to go ahead and plug in everything I have. So dv dt equals pi times 8 centimeters squared times 2 centimeters per second. Now 8 centimeters squared is going to be 64 centimeters squared. And 64 times 2 is going to be 128. So it's going to be 128 pi centimeters cubed per second. That's going to be the rate at which that water is being poured in that cone. Example 6. A 13-foot ladder is leaning against the side of a house when its base starts to slide away. By the time the base is 12 feet from the house, the base is moving at a rate of 4 feet per second. How fast is the top of the ladder sliding down the wall at that moment? At what rate is the area of the triangle formed by the ladder wall and ground changing at that moment? So there's going to be 2 questions that we have to answer here. So I'm going to go ahead and duplicate the slide so I have room to do 1 on each side. So I'm going to start with A, picture. Okay. And I'm going to draw my wall. So here's my wall. I'm going to draw my ladder. Here's my ladder. Here's the ground. Here, I'll put some little rungs on the ladder so it looks more like a ladder. You don't have to be detailed in your pictures. So the ladder's 13 feet. That's not changing. So I'm going to go ahead and label the ladder is 13 feet. The ladder's not going to get shorter. The ladder's not going to be longer as it's moving. The base is sliding away though. So I'm going to call this the base and I'm going to call this the height. Now those are going to be changing because as the ladder slides down, the height's going to be decreasing and the base is going to be increasing to an extent. Eventually it won't, when the height gets 0 and the base gets 13 feet, then obviously the ladder's going to stop moving because it's just going to be flat on the ground. It wants to know how fast the top of the ladder is sliding down the wall at that specific moment. So by the time the base is 12 feet from the house, so that is dB dt. It's moving at 4 feet per second. The base is going to be 12 feet from the house. We're trying to find how fast the top of the ladder is sliding down the wall at that moment, which is going down is going to be dH dt. That's our question. Now I'm pretty sure that we're going to need to know H at that moment. And I can use the Pythagorean theorem to find that out, but I'll wait to do that at the end. So the Pythagorean theorem is what's going to relate all these sides to each other. So we're going to have h squared plus b squared equals 13 squared. And now I'm going to go ahead and find the derivative of this. So 2h times dh dt plus 2b times db dt equals 0. Now I already know what b is and what dB dt is, but I don't currently know what h is, and then I'm looking for dH dt. So I need to figure out what h is, and I can do that by using the triangle at that one particular moment in time. So this is 13, it always is. When the base is 12, we need to figure out what the height's going to be there. So we're going to set up the Pythagorean theorem, and I'm going to do that just kind of down here. So I'll have h squared plus 12 squared equals 13 squared. 13 squared is 169. 12 squared is 144. So 169 minus 144. It's going to give me 25, which means height is going to be 5. So now I'm going to go ahead and plug in everything I know, and that's 5 feet. So I have 2 times 5 feet times dHdt, which is what I'm trying to find, plus 2 times my base, which is 12 feet, times dB dt, which is 4 feet per second, equals 0. So I'm going to go ahead and multiply everything together. So I'll have 10 feet times dHdt. And I'm going to have 4 times 2, which is 8, and 8 times 12. It's going to be 84, I think. Let me double check that. I'm bad with my 12s. Oh, 96. See, I was off. Okay. 7 times 12 is 84. 8 times 12 is 96. So I'm going to have plus 96. That's going to be feet squared per second equals 0. I'm going to move that 96 to the other side, which will make it negative. And then I'm going to divide by 10 feet. So I'll have dH over dt equals negative 96 feet squared per second being divided by 10 feet, which is going to knock down that to just be feet per second. So dH over dt will be negative 9.6 feet per second. So how fast is the top of the ladder sliding down the wall at that moment? It's sliding down at 9.6 feet per second. Negative just shows the direction that it's sliding down. So you can take the absolute value of that if you're just looking for the speed. But if you want the speed with that direction, negative 9.6 feet per second. Now we're going to answer the second question, which is at what rate is the area of the triangle formed by the ladder wall and the ground changing at that moment? So for this one, we're still going to be using that same picture. So I'm going to keep that in mind. But we're trying to find out how fast the area is changing. So the area of a triangle is base times height over 2, or 1/2 base times height. And I'm going to go ahead and see what I know already. So I know that dA over dt is what I'm trying to find. I don't know that. I know dB over dt. That was 4 feet per second. I now know dH over dt. That's what we just found. That was negative 9.6 feet per second. And this is when the base is 12. So B equals 12 feet. And I know also at that time H equals 5 feet. So that's all the information that I have and that I need to know to be able to do this problem. So I'm going to start by finding the derivative of this function. So I'll have dA over dt. Now, on this side, I have two functions. I have 1/2 b and I have h. So I'm going to have to do the product rule. So I'll have 1/2 times h plus 1/2 b. Whoops, forgot my dB dt. Give me just a second. Okay, so 1/2 b is the derivative is 1/2, but dB dt. So I'm going to have a dB dt here. Plus 1/2 b times the derivative of h, which is dH dt. And now I'm going to plug in everything I know. So dA over dt equals 1/2 times h, and h is 5 feet, times dB over dt, which is 4 feet per second, plus 1/2 b, which is 12 feet, times dH dt, which is negative 9.6 feet per second. So I have 1/2 times 4, which is 2, times 5 is going to be 10, and that's 10 feet squared per second. Plus half of 12 is 6, And 6 times 9.6 is going to be 57.6, but negative. So negative 57.6, also feet squared per second. So my final answer here is going to be negative 47.6 feet squared per second. So that's the rate that the area is changing as that ladder is falling to the ground, specifically when the ladder is 12 feet away from the base or from the bottom of the wall, out, and 5 feet at the height. All right, so example 7. So in example 7, we have a spherical ball is inflated with helium at a rate of 100 pi cubic feet per minute. And then we have how fast is the balloon's radius increasing at the instant when the radius is 5 feet, and how fast is the surface area increasing at that instant. So again, another one with 2 parts. So I'm going to duplicate this slide so I have a little bit more room to work. All right, so let's go ahead and sketch a little picture here of what's going on in this problem. And then from there, we're going to figure out how fast the balloon's radius is increasing at the instant when the radius is 5 feet. So let's go ahead and draw a picture. So I have my circle, which represents my balloon. And we're talking about the radius of that balloon. And first we're going to be talking about how fast the balloon's radius is increasing at the instant when the radius is 5 feet. So we're looking for dr over dt. That's our question, specifically when the r is 5 feet. It's a big balloon. And then it's being inflated with helium at a rate of 100 pi cubic feet per minute. So that's going to be my dV over dt. It's the rate of the volume is changing. So 100 pi feet cubed per minute. All right, so when I look at what I have, talking about the volume and the radius, I'm going to use the formula for the volume of a sphere. So volume equals 4/3 pi r cubed. Now I'm going to go ahead and find dV over dt. We already know that. I'm going to plug it in just a minute. And then I'm going to find the derivative over here. I'm going to multiply first. So I'll get 4 pi r squared times dr over dt. dr over dt is what we're looking for. So I'm going to plug in everything I know so far. So I have 100 pi feet cubed per minute. That's my dV dt. 4 pi r is 5 feet. I'm going to be squaring that times dr over dt. So 5 squared is going to be 25. 4 times 25 is actually going to be 100 pi. So I'm going to have 100 pi feet squared times dr over dt equals 100 pi feet cubed per minute. Now if I divide these, I'm going to have 100 feet cubed per minute divided, or 100 pi feet cubed per minute divided by 100 pi feet squared. So when I divide, I'm going to get 1. So I end up with dr over dt equals 1. But it's going to cancel out as far as the feet squared and 2 of the feet cubed. So I'll just be left with 1 foot per minute. That's the dr dt at that specific moment in time. Now, if we found at a different moment, like when the radius was 2 or when the radius was 8, then it's going to be a different value there. But that happened just when the radius was It happened to be 1 foot per minute. All right, so now we're going to do the same thing, but about the surface area. So we already know lots of things now. We found dRdt. And that's 1 foot per minute. We already knew dV dt, which was 100 pi feet cubed per minute. I don't think I'll need that in this one though. And the radius is 5 feet. And we're trying to figure out the surface area, which I'm going to call the surface area just S instead of SA for surface area. So I'm going to say the surface area, I'm going to refer to it as S. So that'll be ds dt will be what we're looking for. Now, this means you're going to have to go to the surface area formula for a sphere. So the surface area of a sphere is 4 pi r squared. Again, I'm just going to call it S instead of SA. So surface area is 4 pi r squared. So I'm going to go ahead and find the derivative now. So ds over dt equals 8 pi r times dr over dt. And now I know everything I need to fill this in and figure out ds over dt. So I'll have 8 pi times 5 feet times 1 foot per minute. So my final change in surface area is going to be 8 times 5 is 40. So it'll be 40 pi feet squared per minute. That'll be how fast the surface area is changing at that particular moment. Now you can think about a lot of applications of this. Can a balloon's, like the structure of the balloon actually change that fast? What kind of material do you need to use to account for that change? Different things like that when you're building balloons or balls or whatever you're building, you need to think about the structure of what you're using to build it. So there's a lot of applications of this and how fast you can fill it up. If you fill it up too fast, it might pop. Maybe you need to fill it up a little bit slower because it can stretch, but it can't change that fast. So that's something to think about when you think about the applications of these problems. Now, in this particular problem, if they only asked us B, but did not ask us A first, we would have actually had to use A to find all the information. We still would have had to use the volume formula to find the rate of change of the radius in order to find the rate of change of the surface area. So sometimes, like this one gave you that in-between step because it gave you part A, but sometimes you're going to have to do that part A step yourself and know that you're going to have to use other information to figure out what you're actually trying to find. So for this example, a light is on the ground 20 meters from a building. A man 2 meters tall walks away from the light directly toward the building at 1 meter per second. How fast is the length of his shadow on the building changing when he is 14 meters from the building? So for this one, I feel like I really need a picture to see exactly what's going on. So we have a building. So this is going to be my building, the wall of the building. Then we have a light out here. So the light and the building are 20 meters from each other. So this distance right here is 20 meters. Now there's a man that is 2 meters tall. So this is the man. He is 2 meters tall. And he's walking away from the light towards the building at 1 meter per second. So his speed is 1 meter per second. So you could think of this in two different ways. You could think of this length right here increasing 1 meter per second, or this length right here decreasing 1 meter per second. I'm going to label this one as like the length that I'm talking about. So I'm going to label this as the ground length. And you're going to see why I did that in a minute. I could definitely label this as G, but it's going to make more sense when we set it up to label this smaller length as G. So that's going to be the ground Then he is casting a shadow on the wall. So this side's going to be the shadow. And I'm going to draw a triangle going from the light to the wall. So that's a triangle, or it creates two triangles technically, a big triangle and a little triangle. So that's kind of what we're looking at there. And this length along the wall is the height of the shadow. I'm trying to erase that. Bring it down just a little bit. Okay. So this is the shadow right there. All right, so when I look at this picture, let's talk about what changes and what doesn't. So this entire length of this triangle right here, this big triangle that was created, that 20 meters does not change. Okay, that length between the light and the building, this side right here, is always going to be 20 meters. Now, the height also doesn't change, the height of the person. What is changing is the shadow and the distance between the man and the light. Those are the two things that are changing. As the guy moves, the shadow is going to change, as well as the distance between the man and the light on the ground. Now, let's go ahead and see what we have and what we know. So the light is on the ground 20 meters from a building. A man is 2 meters tall and walks directly toward the building at 1 meter per second. So this length right here, this G, is growing. So dg dt is going to be 1 meter per second. Okay, that's how fast that distance is growing. And then how fast is the length of the shadow on the building changing? So we're looking for ds dt. That's what we're looking for. When he is 14 meters from the building. Now, when he's 14 meters from the building, that would be this length right here. But we're not using that length in our whole comparison. But if that length is 14, then this length right here must be 6, because the whole length is 20. So if he's 14 from the building, then he's going to be 6 from the light. So G will be 6 meters. That's what we're trying to figure out there. All right, so we need to come up with an equation or a formula that we can use for this particular triangle. Now, we're not going to be using the Pythagorean theorem because we have no information about this length, or we don't even want to know anything about that specific length. But we do have this relationship between the large triangle and the small triangle. The large triangle and the small triangle are actually similar triangles, which means that their sides are going to be proportional. So we can set up proportions with their sides and set them equal to each other. So for example, like this side over this side should equal this short side over the whole short side. Because if they're similar triangles, they should be proportional. And they are similar because they both have right angles and they also both share this angle right here. So you can set up any proportion if you take corresponding sides and make a ratio out of it. So I'm going to do small triangle over big triangle and set up a proportion. So on the small triangle, I have the side that is 2 meters. And on the big triangle, I have the side that is S. So it's going to be 2 meters over side S is equal to small triangle G over big triangle, 20 meters. Now I can find the derivative of both of these, or both sides of this equation. And then I'll be able to use the information I have to find out what I don't know. Now, I'm going to go ahead and make this proportion look a little bit better, and I'm going to cross multiply. All right, so when I cross multiply, I'm going to do 2 meters times 20 meters, which will be 40 meters squared. And then I'm going to have S times G. Now I am going to have to figure out what S is because I am going to have S left after I find the derivative. So I'm going to go ahead and do that real quick before I move on. And I'm going to use my proportion to figure out what S would be. So this proportion that I already had set up, I'm going to figure out what S is when G is 6 meters. So I'm going to have 2 over S equals 6 over 20. And then I'm going to cross multiply, so I'll have 6S equals 40. And then when I divide, S equals 40 over 6, or 20 over 3. I'm actually just going to, I think, leave it as 20 over 3, just because that's going to be a little bit easier when I'm going through and doing the math. So that'll be 20 over 3 meters. It will end up being like 6.6 repeating, but I'm just going to leave it as 20 over 3. All right, so I'm going to go ahead and find the derivative now of both sides. So I'm going to find the derivative of 40 meters squared, which is just going to be 0. So I'll have 0 equals. And then I'm going to have to do a product rule. Whoops. I have to do a product rule on the S and the G. So I'll have 0 equals derivative of S, which is just ds dt, times G, plus the derivative, or just leave S and then multiply by the derivative of G, which would be dg over dt. All right, now I'm going to plug in everything I know. So I'm going to have 0 equals ds dt is what I'm looking for, times G, which is 6 meters, plus S, which is 20 over 3 meters, times dg dt, which is 1 meter per second. Okay, I'm going to move the 6 meters and the ds dt to one side, so I'll have ds over dt times 6 meters equals 20 over 3 meters squared per second. And then if I divide by 6, that 6 is going to join the 3 on the bottom. So it'll actually become 20 over 18, or 10 over 9. So I'll end up with 10 over 9. And one of the meters will go away, so it'll just be meters per second. So the shadow on the wall, when he is 14 meters from the building, is changing 10 meters every 9 seconds, or 10 over 9 meters per second. That's going to be that rate of change. All right. So example 9, we have a right circular cylinder of constant volume is being flattened. So you're squishing the cylinder down. At the moment when the radius is 3 centimeters, the height is 4 centimeters, and the height is decreasing at the rate of 0.2 centimeters per second. At that moment, what is the rate of change of the radius? Now, here's one thing we haven't seen yet, but it says that it has a constant volume. So the volume is not changing. So that's one thing that's going to be important in this problem, is that dv dt is actually going to be 0 centimeters per second, or 0 centimeters cubed per second. So the volume is not changing. Now let me go ahead and draw a picture of this cylinder. So we have a cylinder, so it kind of looks like a can. and it's being squished. So y'all know those videos where like they put something under that big like that big like metal press almost, and it squishes whatever it is. So essentially the cylinder's being squished. It has a radius of R and a height of H. And it says that we know where we're looking for the moment when the radius is 3 centimeters and the height is 4 centimeters. Okay. We know that at that specific moment, the height is decreasing at a rate of 0.2 centimeters per second. So that would be dH dt. So dH over dt is decreasing, so negative 0.2 centimeters per second. And we're trying to find dr dt. So that's what we're looking for. All right, so we're using the volume of a right circular cylinder, which is pi r squared h. So it's essentially the area of the bottom multiplied by the height. So volume is pi r squared h. And I'm going to go ahead and find the derivative of both sides. So the derivative of v is going to be dv dt. And then I'm going to have to do a product rule on the right side of the formula. And I'm going to put the pi with the r squared. So pi r squared will be the first function and h will be the second function. So pi r squared is my first function, and then just h is the second function. So I'm going to start with the derivative of pi r squared, which will be 2 pi r. So dv dt equals 2 pi r times dr dt times h, because h isn't changing. And then I'm going to add pi r squared times the derivative of h, which is dh over dt. So you have to do a product rule. So you take the derivative of the first times the second plus the first times the derivative of the second. Now I'm going to plug it in and then solve for what I'm looking for. So I'm going to go ahead and plug in dv dt, which is just going to be 0. Since it's just 0, I'm not going to bother putting the units. So I'm going to have 0 equals 2 pi r. So 2 pi r is going to be 3 centimeters. And then dr dt is what I'm looking for. So I'm going to leave that there. And then h is going to be 4 centimeters. And then I'm going to add pi times 3 centimeters squared times dh dt, which is negative 0.2 centimeters per second. So I have everything plugged in. Now I'm going to simplify this down. So I have 2 pi times 3 centimeters times 4 centimeters. So 3 times 4 is going to be 12. And then times 2 is going to be 24. So I'll have 24 pi I'll just change it. 24 pi centimeters squared times dr over dt plus, I'm going to have pi times 3 times negative 0.2. Actually, pi times 9 times negative 0.2. So 9 times negative 0.2 is going to be negative 1.8, I think. Should be right. So 9 times 0.2, just double checking my math, is 1.8. So I'm going to have negative, I should just do minus, but it's okay. Negative 1.8 pi centimeters cubed per second. Okay, so I put everything together so far. And now I'm going to move the negative 1.8 pi centimeters cubed per second to the other side. So I'll end up with 24 pi centimeters squared times dr over dt equals 1.8 pi centimeters cubed per second. And if I divide by 24 pi, I'm going to get 1.8 over 24. The pi's will end up canceling out. Also, the centimeters will cancel out. So my final answer for dr dt is going to be 1.8 over 24 centimeters per second. You could divide that out if you wanted to, or leave it as a fraction. As a fraction, I think it's 3 over 40. Let me double check that. Yeah, so you can leave it as 3 over 40 centimeters per second if you want a fraction, or it would be 0.075 centimeters per second if you do the decimal version. So either one of those would be correct for the rate of change of the radius at that specific moment in time. So if you think about this, the height is getting smaller because you're squishing the cylinder down, but the radius is growing and getting bigger. Not that much bigger, not that fast, but I mean, of course, the height isn't changing that fast either. It's just going down 0.2 centimeters per second. So the radius is increasing 0.075 centimeters per second. So a little bit slower. All right, so example 10, we assume that sand is allowed to pour onto a level surface to form a pile in the shape of a cone with a height equal to the diameter of the base. If sand is poured at a rate of 2 cubic meters per second, how fast is the height of the pile increasing when the base is 8 meters in diameter? All right, so let's think about this. We have a cone. So, but it's a cone-shaped pile of sand. So I'm going to draw this, and it says that the height is equal to the diameter of the base. Let me see if I can draw this kind of to scale. So we have this cone pile of sand, and the height of this thing is equal to the diameter of the base. So we have the height, we have the diameter of the base. So that's the whole length of the base. And then we have the radius of the base as well. Okay, so we have the diameter, which is that whole length. So this is diameter, and then half of it would be the radius. And I'm going to go ahead and label the radius there because when we set up the formula for the volume of a cone, it's 1/3 pi r squared h. So you're going to want the r as part of it. Okay, so let's go ahead and look at what we have. So the height's equal to the diameter. So I'm going to say the height is equal to the diameter. That also means the height is equal to 2 times the radius, or the radius is equal to the height over 2. So those might be useful when we set up our formula. And then if the sand is poured at a rate of 2 cubic meters per second, so that's volume. So the volume, dV over dt, is increasing 2 cubic meters, so meters cubed per second. How fast is the height of the pile increasing? So we're looking for dH over dt when the base is 8 meters in diameter. So when the diameter is 8 meters, which also means the height is 8 meters, and it also means the radius is 4 meters. So lots of different things we can kind of look at when we're going to set up this formula. Since I'm looking for dHdt, that's what I don't know. I think I'm going to get the volume formula to be in terms of H. So I'm going to go ahead and work on setting this up. So I have the volume is equal to 1/3 pi r squared h. But instead of writing r squared, what happened? Okay, and instead of writing r squared, I'm going to replace r with h over 2. That way, I will only have h's in my formula because that's what I'm trying to find. I'm trying to find dh dt. And I don't know dr dt. So I'm going to rewrite my formulas to only have h's in it. So I'm going to have volume equals 1/3 pi. And I'm going to have h over 2 squared times h. I'm going to clean this up a little bit. So volume equals 1/3 pi h cubed over 4, because I have an h here and I have 2 h's there, and I also square the bottom. And then I'm going to clean it up a little bit more. I'm going to put the 4 with the 1/3 and make that 1/12 pi h to the 3rd. And that's volume equals. I should have brought that volume equal over. But volume is equal to 1/12 pi h to the 3rd. For this particular shape. That's not for all cones. All right, so let's go ahead and take the derivative of this formula with respect to t. So I'm taking the ddt of both sides. So I'll have dv dt is equal to, I'm going to do 3 times 1/12, which will be 3/12 or 1/4 pi h squared times dh over dt. And now I can plug things in. dv over dt is 2 meters cubed per second equals 1/4 pi. H is 8, so 8 meters squared times dh dt, because that's what I'm looking for. Okay, I'll have 2 meters per second, or meters cubed per second, excuse me, equals, okay, if I square 8, I get 64, and 64 over 4 is going to be 16. So I'll end up with 16 pi meters squared times, I put cubed, meters squared, I hate how laggy this thing gets when I'm making a video. Erase. There we go. Okay. Let's see if it'll change back. So that's meters squared times dh dt. And then if I divide by 16 pi, the meters will cancel out. So I'll just have meters per second. And I'll have 2 over 16, which will be 1 over 8 pi. So dh over dt will equal 1 over 8 pi meters per second. So that's how fast the height of the pile is increasing at the time when the base is 8 meters in diameter. Problem. Example 11, an aircraft is flying at an altitude of 3 kilometers at a speed of 600 kilometers per hour in a direction away from a tracking station. How fast is the angle of elevation changing when the aircraft is over a point 8 kilometers from the station? So I'm going to draw a picture for this one. So we have an aircraft that's flying at an altitude of 3 kilometers. So here's that path of that plane, and I'm going to call that path X. And that path is 3 kilometers off the ground, and it's going to stay that way. It's a constant height of that plane. I'm going to connect this to make this triangle. So here's the tracking station. It's going to be down here. And the plane is flying away from the tracking station in this direction. And we're trying, so here's a little airplane in the sky. Kind of looks like a fish, but that's an airplane. All right, so we're trying to figure out how fast the angle of elevation is changing when the aircraft is over 8.8 kilometers from the station. So when this length right here is 8 kilometers, that's when we're trying to figure out what the angle of elevation is going to be changing by. Now, that means that x will also be 8 kilometers at that point. This is the angle of elevation, but it's going to also be equal to this angle, which is called the angle of depression. And I'm going to call that angle theta. So these two angles are going to be equal to each other. So if I figure out how fast the angle of depression is changing, I also figure out how fast the angle of elevation is changing. So x is 8 kilometers. Dx dt is going to be 600 kilometers per hour. And we're trying to find the rate of change of the angle, which is d theta dt. Now, we don't know what this is, but I can think about what it would be in. So when an angle changes, an angle measurement is radians. So this is going to be radians per hour. Now, that's a completely different unit than what we started with. So we're talking about kilometers in the problem, and we're trying to relate that to radians. So when I plug in the units, they're not going to cancel out nicely like they did in the other problems, because the units were related more closely, like meters and meters cubed end up, matching up. But here we're going to get radians per hour as our final unit. So I'm not going to plug the units in when I figure out this problem, because they're not going to end up canceling out and turning into radians, because we're not starting with radians. But I'm going to go ahead and try to set up something to relate the angle to the sides, which is going to be our right triangle trig. So if this is the angle that I'm looking at, this is going to be the opposite side from the angle, and this is going to be the adjacent side. So when I'm talking about opposite and adjacent, I'm talking about tangent. So this is the function that we're going to be doing is going to be tangent of theta equals the opposite side, which is 3, over the adjacent side, which is going to be x. I'm going to go ahead and rewrite this as tangent of theta equals 3x to the negative 1. And then I'm going to go ahead and find the derivative with respect to time. So I'm going to have the derivative of tangent, which is going to be secant squared theta times d theta dt, equals negative 3x to the negative 2 times dx dt. And I'm going to rewrite this. I'll have secant squared theta times d theta dt equals negative 3 over x squared times dx dt. All right, so there's my function. Now, I am solving for this, so I don't know what it is, but that's okay. I do know what x is, and I do know what dx dt is, so I can plug those in. But I have this secant squared theta that I don't know what it is. So I'm going to use the triangle and figure out what secant squared theta would be. Now, secant squared theta is the same thing as secant of theta squared. And secant of theta is going to be the same thing as the inverse, not the inverse, the reciprocal of cosine. So cosine is adjacent over hypotenuse. So secant is going to be the hypotenuse over the adjacent side. So if we're talking about theta, the adjacent side is going to be x, but that's going to be 8 at this point in time. And the hypotenuse is going to be this side down here, which I currently don't know what that side would be at that particular moment in time, but I can figure it out by using the Pythagorean theorem. So I know that this side's going to be 8, and this side is 3. So I have 8 squared plus 3 squared, which is 64 plus 9, which is 73. And then if I take the square root of that, it's going to be the square root of 73. That doesn't simplify down nicely for us. So the hypotenuse is going to be the square root of 73, and the adjacent will be 8. So this will turn into, it's going to be the hypotenuse, which is the square root of 73 over 8 squared, which will end up being 73 over 64. So 73 over 64 is the value of secant squared x at that particular moment in time. So I'm going to have 73 over 64 times d theta dt equals negative 3 over 8 squared times 600. Now, I'm going to end up with 64 on the bottom over here as well. So I'll have 64 on the bottom of both sides. So when I flip this function around and multiply, those 64s are going to end up canceling each other out. So I'll have d theta over dt equals negative 1800 over 64 times 64 over 73, which is going to be negative 1800 over 73, and that'll be radians per hour. And you can write that as a decimal as well. I'm not sure what it would be. So as that plane is flying away, that angle is actually going down. Okay, the further the plane goes away, the smaller that angle is going to get. Because you're looking the angle here, like if the plane's here versus the plane being here, that angle is going to keep getting smaller. So it is changing negatively. When you're moving away, the angle of elevation will be going down. All right. So now we have a problem that is a related rates problem, but it's relating the x and the y value of a hyperbola. So a particle moves on the hyperbola, or hyperbola. I think a hyperbola is more of the math term. X times y equals 18 for time t is greater than 0 seconds. At a certain instant, when y equals 6 and dy dt equals 8, which of the following is true about x in this instant? So you can see that we've taken the derivative with respect to time, with respect to t. So I'm going to go ahead and actually take the derivative of this function. Okay, so our function is x times y equals 18. So I'm going to go ahead and find the derivative of the first, which is x, which would be 1 times y. So 1y times dx dt plus 1x times dy dt equals 0. Now, I know what dy dt is, and I know what y is. And I'm looking for dx dt, but I currently don't know what x is at that moment, but I can figure it out. So if y is 6 and x times 6 equals 18, then x is going to be 3. So I'm going to go ahead and plug that in. So I'm going to have 6 times dx over dt equals 1x, or 3, not equals, plus, plus 3 times dy over dt, which is 8, equals 0. So then I'll have 6 times dx over dt equals negative 24. So I'm going to move that over. So dx over dt is going to be negative 4. And for this one, time is in seconds, so that will be units per second. So it's going to be decreasing by 4 units per second because it's negative 4 units per second. So that will be this answer right here. Now, the way that you knew that this was a related rates problem is because you're taking the derivative with respect to t, and t is time. So you're trying to figure out how the different values on that function are changing with respect to time as that particle's moving along that particular graph. All right, now we're going to see another problem. So fuel consumption of a car in miles per gallon, or MPG, is modeled by f of s equals 6e to the s over 20 minus s squared over 2400, where s is the speed of the car in miles per hour. If the car is traveling at 50 miles per hour and its speed is changing at the rate of 20 miles per hour squared, what is the rate at which the fuel consumption is changing? So we're trying to figure out how the fuel consumption is changing. So I'm going to call that df dt. So df dt is what we're trying to figure out. That's the unknown. But it says that the speed, so speed in this problem is s. So it says that the speed is 50 miles per hour. And it said the speed is changing. So the change in speed, which would be ds dt, is 20 miles per hour squared. Now, when we look at df dt, df dt is the rate at which the fuel consumption is changing. So if you look at all the answer choices, the units are miles per gallon per hour. So just like with the radians problem, since we're in miles per gallon per hour, it's a completely different measurement than the ones that we're using in the actual problem. Because in the actual problem, we're doing miles per hour. We're not doing anything with gallons. So when I plug this in, I'm not going to worry about plugging in the units because I know my final units, whatever I get, is going to be miles per gallon per hour. So I'm going to go ahead and work on taking the derivative with respect to time of this function right here. Now, this side where it says f of s equals, I'm just going to refer to that as just f equals. Instead of writing df of s dt, I'm just going to write df dt. So the derivative of f is going to be df dt equals, now I'm going to take the derivative of the right side. So I have a chain rule here, so I'm going to just repeat what's there already. So I have s over 20 minus s squared over 2400. And now I'm going to multiply by the derivative of the inside here. So I'm going to have a multiplication here in a parentheses, and I'm going to do the derivative of s over 20. I'm going to erase this right here just so I have a little bit more room. I'll rewrite that over here. I'll write it, well, over here. So ds over dt equals 20 miles per hour squared. Okay, so I'm going to go ahead and take the derivative of s over 20, which is going to be 1 over 20 times ds over dt minus, now here I have 2, which is going to come out in front, so I'll have 2 over 2400 times s times ds over dt. Now, I have values to plug in for ds over dt. I'm going to be plugging in 20. I'm going to be plugging that in here and here. And for s, I'm going to be plugging in 50, and I'm going to plug that in here, here, and here. So I'm actually going to do all of that work in Desmos, because if you look at our answer choices here, they're all decimals, and those are going to be, this is actually a calculator active problem. So I'm going to plug them all in, but I'm actually going to do the math in Desmos. So I'm going to go ahead and set them up. So I have df over dt equals 6e. Now, the exponent is going to be s, which is 50, so it'll be 50 over 20 minus, and then 50 squared over 20. Or not over 20, over 2400. Okay, so that's going to be my exponent there. I'm not going to do the math. I'm just going to plug it into Desmos in just a second. And then I'm going to times that by 1 over 20 times ds over ds dt, which is 20, minus 2 over 2400 times s, which is 50, times ds dt, which is 20. And then I'm going to take this whole entire piece right here, and I'm going to type it into Desmos, and my solution should be one of these answers that are these choices down here. Okay, so I'm going to go ahead and type in that function. So I'm going to have 6e, and then my exponent, I'm going to put parentheses, and I'm going to have 50 over, whoops, not 50, or not 20, but 50 over 20 minus 50 squared over 2400. That's my exponent. Then I'm going to come down, and I'm going to multiply and have a parentheses here, and I'll do 1 over 20 times 20 minus 2 over 2400 times 50. times 20. All right, and you'll see I get 4.2987, which will be 4.299. So right here, the solution will be B. Right here. All right, so that's how you would do that problem. You would take the derivative with respect to t, but then plug in everything you know and use Desmos to help you do that final math and not having to do all of that by hand, which we couldn't even do because we can't raise e to a random number by hand. That would be too difficult.